All right, so number 14. So it's find a polynomial with integer coefficients, satisfies the given conditions. Has degree 5. Okay. Has a 0 of 1/2, a 0 of -3. Has a 0 of -I. Okay. We want a leading coefficient of 4. And the 0 of -3 has a multiplicity of 2. All right. So if that's the case, then we're looking at, if this is a 0, so x minus 1/2 is that, right? If that's a 0, then we have x minus that as a factor, but it has a multiplicity of 2, correct? So that's that. -I is a 0, so x minus that, so that's plus I. What else is going to be a 0? X minus I, conjugate, okay? Now, some people have been asking, well, how do I know what it's not if it's not A plus BI? Well, it is if you write it this way. 0 minus I, right? Now, is this conjugate 0 plus I? Which is just I. Okay, so we got that. Now, I would be kind of maybe intelligent about how you multiply these out. You can just put these as 5 factors, multiply your first 2, multiply your second 2, or your second grouping of 2, and keep going. You can be kind of unintelligent about it and still get the right answer. Well, doesn't it make sense to multiply those two? If I multiply those, it gives me x squared plus 1. Okay, it gives me -I squared, right? -I squared is positive 1. Now I'm going to look at this one. Doesn't that give me x squared plus 6x plus 9? And then I've got my x minus 1/2. All right, so I still, I've gone down from maybe 5 linear factors now to 1 linear and 2 quadratic, right? So it's a bit simpler in regards to the number of factors I had. So let's keep multiplying. What do you want to multiply? Which ones do you want to do? Okay, you want to do these two? Okay, that's fine. So you're going to go x squared times x squared gives you x to the 4th. X squared times 1 gives you x squared. 6x times x squared gives me 6x cubed. 6x times 1 gives me 6x. 9 times x squared, 9x squared. 9 times 1 gives me 9, right? I think I would, because I still got this x minus 1/2 out here, I think I would probably condense this first, right? You don't need to, but you probably should. Let's see, that's going to be x to the 4th plus 10x squared. Plus 6x cubed. I know I'm not in the right order, but does it matter? No. And then plus 9, so that's combining my terms, and now I've got x minus 1/2, right? So let's run x through there, so it's going to be x to the 4th times x, which is x to the 5th, x times 10x squared would be 10x cubed, right? So this x is just going to keep everything the same here except change the exponents, right? So we'll go through that real quick. It'll be plus 6x to the 4th plus 6x squared plus 9x. Now I'll multiply through by the -1/2. Gives me -1/2 x to the 4th minus 5x squared minus 3x cubed minus 3x minus 9/2. I get them all? All right, so now go through and combine like terms. X to the 5th. And use, do I have here x to the 5th? Nope. X to the 4th. 6x to the 4th minus 1/2 x to the 4th, right? Okay. The 5.5 x to the 4th, right? You can either write that as 5.5. Okay, or can I write it as 11/2? Both those. So now I go x to the third, so everything else should be pretty nice. So x to the third minus 3x to the third, so give me what? 7x cubed? Positive 7x cubed? 6x squared minus 5x squared is x squared. 9x minus 3x is 6x. And minus 9 halves. Okay? Now, I have to abide by the rules. It has to be degree 5, 0 is 1/2, negative 3. Leading coefficient needs to be 4. So how do I make the leading coefficient 4? Multiply by 4. I can't just, here's what people are wanting to do. Well, they get this and say, okay, a 4 on there. Okay? Well, if I still have a 4 on there, that ultimately changes these zeros. Does that make sense? It's going to change all of these little individual factors, which were generated through these original factors, which were generated through these zeros, right? If I just change one term, it changes all of those things. Okay? So I can't do it that way. But what we do know is that through transformations, multiplying an entire function by some number will maintain the same exact zeros, right? Because when I multiply by a scalar multiplier out front, it just changes all the y values, right? Well, what are the y values for all of these things when I look at the graph? Now, careful. When I look at the 0 of 1/2, what is the y value at 0, right? So the idea is multiplying by 4 to the entire thing is going to keep those at 0, because when I alter their y values, what's 0 times 4? So 0. That keeps the same x-intercept. So what I have to do is multiply everything by 4. So when you do that, you give me 4x to the 5th, 22x to the 4th, 28x squared, 4x squared, or 28x cubed, 4x squared, 24x minus 18. Okay? So that's the approach that we need to take on that one. Yep. All right, so degree 4. Okay, zeros of I plus 1, constant term of 12. Okay. Before we get into this, would be a really hard question, guys, for me to give you in the reverse order. If I gave you 6x fourth minus 12x cubed plus 18x squared minus 12x plus 12, and I asked you to graph that, find the zeros of that, you can't do that right now, because your catch-all technique is P over Q, right? P over Q is called the rational root theorem, correct? Meaning that the solutions are on the real number line, right? Now, they're not everything that's on, because you could have irrational zeros, which the rational root theorem would not target either. But this, because all my zeros here are imaginary or have imaginary components, okay, they're complex numbers in the form a plus bi. If I asked you 6x to the 4th minus 12x cubed and asked you to graph that thing initially, you can't do that, because your factoring tools right now, your factoring techniques right now, exhaust that P over Q, right? Okay, and we'll kind of talk about that as we continue to see a couple more of these examples. All right, but going from this route, we're saying we got a 0 of I. So what's another 0 if I is a 0? Negative I. If this is a 0, what is 1 minus I? Okay, so we should have factors then of x minus all those things, right? So x minus I, x minus negative I, and then x minus 1 plus I, and x minus 1 minus I, right? And that's the best way to write that initially. I'm going to then take these two back here, distribute the negative through. And we talked about in class then that you would want to group those two terms and those two terms, because if I did that, is this now a set of conjugates? Yeah. Okay. What are these two going to multiply together? Give me x squared plus 1. These two are going to multiply together. So I'm grouping these. It's going to give me x minus 1 squared, right? And now negative I times positive I gives me negative I squared. Well, what's that same as? Plus 1. All right, so now we've got x squared plus 1. This thing is going to turn into x squared minus 2x plus 1 plus 1, right? We'll make it plus 2. And that's kind of what I was saying at the beginning. If I were to start you off with 6x to the 4th minus 12x cubed plus 18x squared minus 12x plus 12, you're going to have to get to this somehow from that. That's going to be kind of hard for us to do. Okay? But now going this route, going through formulaing here, we can go through one more step of multiplication. So I have x to the 4th plus or minus 2x to the 3rd plus then 2x squared plus then x squared minus 2x plus 2. Combine like terms gives me t of x to be x to the 4th minus 2x cubed plus 3x squared minus 2x plus 2. All right. Now, that is not our answer, right? The directions say that the constant term has to be 12. If I look for t of x, I just wrote down at the bottom, what is my constant term? 2. Okay? What's a synonym for a constant term in t of x or any polynomial? Y-intercept. Okay? Remember seeing a question on Wednesday where we did this, but instead of using the constant term word, I used y-intercept. If we go back to our quiz, I gave you the picture. 0 and negative 4 was the y-intercept. This is the same question. It's just using different vocabulary, right? And that's the thing that people don't kind of grasp onto and think that's important in a math class is the vocabulary, okay? Well, the vocabulary is what structures and tells you what you need to do and how you need to approach the process. Does that make sense? Okay? You know, if you can be the best algebra student once shown kind of a process or shown the algebra work, I guess, that the handwritten information, if you were to see this and they provided that, you could be the best algebra person and always be able to come up with that, right? Okay? But if I don't know my vocabulary, I'm going to get the question wrong, okay? And that's here on out in every math class that you guys ever take. And geometry tried to help you kind of explore that and understand that. You guys agree geometry had a lot of vocabulary in it? And maybe the main reason why geometry was troublesome for us, because we, in a math class, up till 10th grade, we're probably trained to just do the math. Don't worry about any of the English part of it. Don't worry about the vocabulary, okay? And I'm not saying that you were taught to not worry about it, but it was just something that you guys laid and you were shown, this is how you do it. When you see this, this is how you do it, okay? Well, when you get to higher level math, guys, it's kind of the reverse. It's now they're using terminology to get you to understand what you need to do and when you need to do it, okay? So that 2 has to become a 12 for us, okay? I see a lot of people can say, well, add 10 to that, okay? Well, if I add 10 to that, think about how that 2 generated right here. That 2 generated by taking that number right there, 1, and that number there, 2, and multiplying together, right? Okay? Well, if I just add 10 to that and make that 12, that would have meant that that 1 and 2 in that red line would have had to either be 1 and 12 or 2 and 6 or 3 and 4, right? Okay? And we also have the ability, they could have been negative, both of them been negative or something like that. Well, if that's a 2, and that would have been a 6, would these things have been different? And if those things would have been different, would these things have been different? And if these factors would have been different, would those have been the zeros? No. Okay? So you can't just add something to the polynomial, because that's going to kind of contradict what we thought our initial zeros were, okay? But what can I do to everything? Multiply by 6, and that's what we're seeing right here, okay? We can do that vertical stretch because that doesn't impact the x-intercept. It keeps our y values at 0 at those points. That make sense? Okay. As we're doing some of these problems and hopefully starting to realize, I want to do one more with you to express or explain the last concept in this section 3.5. Yes.
So whenever we multiply, it just changes the numbers. It can't change the zeros.
Yes. Yes. So if I look at question number 5, and this is the idea, this is the concept so far, basically this whole course, is trying to develop tools for factoring, right? And P over Q is kind of, like I said, the catch-all for the most of it. So I would say we've probably got like 90% of our polynomials that we'll ever see, we have the ability to factor them. And there are a couple out there that linger that maybe we can't yet. Maybe we need some calculus to do that, but we're going to have most of our polynomials factorable, okay? We talked the other day that we should kind of have a list of factoring techniques kind of in our mind. I would think that GCF would be the first thing that I try, okay? I would then look for something that's quadratic, okay? And we'll write quadratic form because it doesn't just have to be squared. It could be x to the 6 or x to the 8 or something like that. When I say quadratic form, remember this. I think I did write this for you guys last week. Ax to the 2n plus bx to the n plus c. And that means you could have something like 2x to the 4th plus 3x squared plus 8. That's a quadratic form, right? I'd be looking for those types of things, okay? Because those are going to allow me to factor much quicker than anything else, okay? The next thing I would look for, if quadratic form is not there, I would try factor by grouping, okay? And traditionally, I think unless you have like a really kind of unique case, usually factor by grouping, we're going to look for an even number of terms, okay? I could have 5, and when I group 3 of them, I get like a perfect trinomial, and things can work out, but that's going to be very rare. So I would be looking for even amount of terms. So in this one, factor by grouping would not work, okay? 5 be not something that I don't even pay attention to if I don't have even terms, okay? Or even quantity of terms. And the last thing should be then our P over Q. Now, as we do problems, guys, as we work through any and all factoring problems, I'm not saying that once I choose that I'm going to use a GCF, that that's the only factoring technique that's going to be working here, okay? I might choose a GCF and realize, okay, it made things simpler, but now I got to look at factor by grouping. Or now I've chosen the GCF, I pulled that out, and now I got to do P over Q, okay? Or maybe I did maybe something with quadratic form. Maybe it was like x to the 12th or something like that, and I recognize that's quadratic form. Well, now I broke it down to like x to the 6th, okay? Well, now maybe P over Q is going to address that quadrant or that new polynomial of x to the 6th. Does that make sense, everyone? Okay? So you might have to kind of piggyback some of these things off of one another, okay? I think the GCF is awesome, okay? If I can pull out a variable term is best, okay? But a coefficient is nice as well, because that will eventually, if I have to go to factor by grouping or P over Q, having that kind of multiplier pulled out will make my list of P over Qs simpler. So if I look at this one, I'm going to pull out what? X, okay? So I'm going to have x times x squared minus 6x plus 10, okay? Now, here's why I want to talk about this. It's going to wrap up the last of section 3.5, is that we have a theorem that says every single polynomial can be broken down to a series of linear factors, okay, which we talked about I keep saying last week, but Monday or Tuesday. We said every single polynomial we come across can be broken down to 5th degree. We can write it as 5 factors. Okay, and those zeros may be real numbers or they may be complex, right? A plus BI. And we talked about that. We've done a lot of examples of that. Okay, this theorem is kind of a. I would think that this theorem is kind of on our way to that. Okay, so it's kind of maybe. I think it would be better placed if we would talk about this theorem prior to the complex zeros theorem. And basically says every polynomial that you ever come across can actually be broken down to a product of linear factors and what we call irreducible quadratic factors. Okay? You guys remember back into Algebra 1 when you were first learning how to factor, and when I looked at this number 10, I said, okay, 1 and 10, 2 and 5, right? None of those in any plus or minus version will have to give me -6, right? So that you write prime next to those. Remember doing that? Okay. So that essentially tells us that was a irreducible quadratic factor. Okay. Every polynomial we ever come across can be written that way. Okay. Think back to the one we just did. Okay. The 6x to the 4th one. I don't remember. I think it was maybe the first question we did, where all the zeros were a plus bi form, right? Okay. Well, once we started multiplying those out, didn't we get 2 quadratics that those a plus bi came from? Okay. So and this is the relationship. Whenever I have irreducible quadratic factors, I should still be able to work through those and find their linear factors through the what? If I continue to factor x squared minus 6x plus 6. Quadratic formula, right? 6 plus or minus 36 minus 4 times 10 all over 2, right? And I think I need x. Okay, so I've got now 6 plus or minus -4 under my root all over 2. What's -4 underneath my square root? 2i. So you're going to go 6 plus or minus 2i all over 2. That's going to give me 3 plus I, 3 minus I, right? This idea, the quadratic formula, guys, and how we complete the square is kind of the basis of why complex a plus bi zeros show up in pairs. Okay? They can only show up in pairs. They can't show up in triplets. They can't show up in quadruplets or anything like that. They show up in pairs because of the quadratic formula. Is that all right? Okay. So if they do show up in pairs, kind of working our way backwards, doesn't that mean if that one there, or that pair of 3 plus I and 3 minus I, had to come from a quadratic factor, right? Had to come from, and there's an irreducible quadratic factor. So if I had, another set of, maybe I had like 2 minus 3i and 2 plus 3i. Wouldn't that have come from a quadratic factor that was irreducible? Okay. So because they come in pairs, that idea means that every single p of x that we come across can always be written as a product of irreducible quadratics if it does indeed have a plus bi zeros. Okay. So that's kind of something to think about. Why is that useful? Well, let's go down to come on, find that 6x to the 4th one that we had. That one, okay? What this means is if I have, some p of x that is 6x to the 4th plus, now I don't care what is kind of at the end of that, okay? But what we're finding out here is that what we're talking about is that we could have 4 real zeros, right? That says zeros. We could have 4 real zeros because it's a 4th degree polynomial. Cross the x-axis 4 times, right? If I have 4 real zeros, how many imaginary zeros, or how many a plus bi zeros would you have? 0. And I'm going to call them non-real. So 0 non-real. Okay. Can I have 3 real zeros? No, because that would mean I have 1 non-real, right? But 1 non-real would be that situation where we use the irreducible quadratic, right? We know that they should be coming in pairs, correct? The a plus bi come in pairs. So I could either have 4 real zeros, 2 real zeros. If I have 2 real zeros, then I have 2 non-real. Okay. Now, these two are types of P of X's that they can start us with, and we can work through and find all factors, right? All linear factors. Because once I use P over Q to find two real zeros, now I have a irreducible quadratic that I have other tools to kind of factor. But could I have 0 real zeros? How many non-real zeros would I have? 4. And that's kind of what's happening here with this one. That has 4 non-real zeros. If I started you with that and asked you to factor it, you don't have the tools to do that. Because P over Q is going to give me rational zeros, and rationals are real numbers, right? Okay? So P over Q would not give me anything, plus or minus the factors of 12 divided by plus or minus the factor 6. None of those will work. So it's not going to depreciate that thing down to a cubic or a quadratic that I could then continue factoring with. Does that make sense? Okay. So we couldn't really address a P over X right now, provided that it had that kind of situation occurring. Same thing happens if I had like 6x to the 6th. I could have 6 reals, right? And 0 non-real. I could have 4 reals and 2 non-reals, right? So I could address those two. We have the tools that allow us to do that. But once I get to 2 reals, which we have the tools to find the 2 reals, I would have 4 non-reals, right? And those 4 non-reals would be listed after I do my P over Q stuff to find the 2 reals. My 4 non-reals would be kind of listed in a x to the 4th, which kind of this thing here would default me down to that situation. Does that make sense? And I can't factor that. I don't have that ability. And then I could have 0 reals and 6 non-real solutions, and I'd have trouble with that. Same thing happens with odds, though. Okay. But every odd polynomial, odd degree polynomial, so like 6x to the 5th, that has to do what? 6x to the 5th has to do what? Any odd degree polynomial has to cross the x-axis. Okay. So the situation where I was seeing that I had all non-real zeros and I had no real zeros, those were curves that never crossed the x-axis. But every odd one has to. Okay. So I could have 1 real zero. Okay. How many non-real? I could have 4 non-real. That'd be hard to deal with. Okay. But I could have, could I have 2 real zeros for? Not if we're counting multiplicities, right? Okay. If we're counting multiplicities, I cannot have 2 real zeros. So if I could have 3 though, right? I have 3 real zeros. For some reason, I can't write the word zeros. And then I would have 2 non-real, right? Okay. What do we? I don't know. What can we make? What argument can we make about our non-real all the time? They're what kind of number? They are. Oh, so non-reals, yeah, they are A plus BI, but just in terms of their quantity, how many? It's always an even number, right? It's either 0 or an even number. So that then kind of dictates then how many reals we have to have based on what P of X's leading degree was, right? Does that make sense? Okay. Just little things like that, guys, I think is the math that we should be interested in. Not so much can I calculate, okay? Because at some point you're going to find out, you're going to go to a math class and you're going to say, okay, I already know all this. I've learned enough math, I've learned enough algebra, and I'm versed in it, to where now I can use software. I can use computer programs to help me do the expansion, to help me do the division and to do the factoring and all that kind of stuff. And eventually, after you get past calculus, you say, I can use software now to do all the derivatives and all the slopes and all kinds of stuff. Now it's a matter of what is that stuff, what is all that analytical math telling me, and how do I analyze it and develop relationships between it? Does that make sense? That's the math, okay? After peers that have taken stats, okay? Stats is not
a calculation-based course, or should not be a calculation-based course. You should not be doing a lot of work mathematically or algebraically in stats, okay? Now, they might, when I taught stats, and what I would do is I would initially kind of break people into the process that our calculator was going through. So I would start to say, okay, we're going to do like standard deviation and variation or variance and that kind of stuff. We'll do it by hand. And those formulas are really long and pain in the butt. Okay, and I'll do it by hand. So it gave them an appreciation for what your calculator was doing. And then we started to work then in Excel and started to let Excel do all the work for us. But now that would progress into, there's a lot of stats programs out there where you just basically type in your information, type in a cell your data, okay? And then you go do it in a drop-down menu. Say, okay, I want a T-chart, or I want a P-chart, or I want a chi-square chart, or something like that. And it does all the data for you. It does all the calculations for you. It gives you all your results. But it doesn't tell you how to read those results, what it means to you. Does that make sense? That's the math. What does everything mean to me? What are the results telling us? And that's kind of a, hopefully when you took geometry with me was the mindset that I was helping you, or hoping that you